Hi everyone, welcome to Culture. So in this session, we are going to discuss about the most misunderstood topic is reactive power. Right? So what is reactive power and where it can be applicable? What is the role of reactive power in different applications like power systems, machines, power electronics? So let us discuss from the basic to the advanced level. Now, let me start with what is the reactive power function. So generally in a power systems, so we will use the reactive power control in the power system to improve the power quality. So power quality in the sense, so it improves the voltage regulation, so it improves the power factor, and it improves the stability also. Like it has a different applications. Let us explore one by one. So let me start with the basic thing. What is reactive power? So let me start with the power triangle. Very basic is power triangle. So let me start with the power triangle. So we have the different powers in electrical engineering. What are those powers? So we have the apparent power, right? So we have an apparent power. Let me denote as S. Right? And we had an active power or the real power. So let me denote with the P. And reactive power, let me denote with the Q. Right? So let us take the power triangle. So how we can represent in the power triangle? So the horizontal axis is P, which is an active component of apparent power. Right? So which is reactive component of or imaginary component of apparent power is Q. So now, so let me assume this angle is pi or theta. Whatever be the notation you can assume. Right? So now in this power triangle, so we can derive the apparent power. So what is the apparent power? So in a complex notation it is, so S equal to P plus JQ, S equal to P plus JQ. So if I want to find the magnitude of the apparent power, so I can find from this root of P square plus Q square. Right? So how can I find the power factor? So power factor equal to, so P by S, that is active power divided by apparent power. So and so if I want to find the pi itself, I can find from the tan inverse of Q by P. So up to here, so we know about the reactive power. So we can find the reactive power from the power triangle. It is very basic and very fundamental level. Even BTech first year student also can answer this, all these things. Now, beyond this. Now, so let me take the single line diagram of the power system. So it has the generator. So it has the transmission line. Assume that it is a transmission line. We have the inductive load and capacitance here. Two loads are there, inductive load and capacitive load. Assume that. Now, so what we will do here is, so we will find the reactive power polarity. We will find the reactive power polarity. For example, now if I take, let me take it for the inductive load. This side I will take it for inductive load. Right? So inductive load, this side I will take it for the inductive load or inductive load. Otherwise, I will take it for the generator side. Right? So I will take it for this side is generator side. Refer to the generator side. And this side I will take it for the refer to the load side. Refer to the load side. Load side. Now let us take the load side. For example, if I close the switch to the inductive load. So what happened? Now generator is connected to the inductive load, whether it is induction motor or induction furnace. So whatever it may be, so it is an inductive load. So in case of inductive load, as we know that the current lags the voltage, it operates under lagging power factor. Now, if it is an inductive load, So what is the polarity of the reactive power? So we are assuming it as a positive. If it is inductive load, the reactive power polarity is positive. Now let us taking the, we are analyzing for the inductive load. Inductive load. So if the Q is positive means, remember this point, if Q is positive means, so inductor or inductive load absorbs lagging reactive power. Lagging reactive power. Lagging reactive power. So for example, in case of, with respect to generator, if I want to speak with respect to generator, so what I need to write? Again, when it is connected to the inductive load, here also let us take the inductive load. Inductive load. So what we need to write? So here Q is positive, but what is the thing here? Generator delivers the reactive power. Generator delivers lagging reactive power. Lagging reactive power. Generator delivers lagging reactive power. Very simple, very simple. Try to understand from the very fundamental. So the polarity of inductance is, the polarity of reactive power is very important to analyze. So in case of inductive load, so what we need to take? So inductor absorbs lagging reactive power and the polarity of the reactive power is positive. So if I speak same thing with respect to generator, so the generator delivers reactive power and the reactive power polarity is positive. Now, for example, if I move this switch to the capacitor load, now the generator is connected to the capacitance, right? So now load is capacitor load. In the second point, load is capacitor load. Load is capacitor load. So Q is, if it is capacitor load, Q is, what is the reactive power polarity? The reactive power polarity Q is negative. Q is negative. It absorbs leading reactive power. It absorbs leading reactive power. Absorbs leading reactive power. Leading reactive power. Now, for the same thing, if I want to mention through the generator side, so with respect to generator, if I want to speak, so in case of capacitive load, so if I want to mention through the generator, so how I can mention? So here Q is negative, that is reactive power is negative, and it delivers the leading reactive power. It delivers leading reactive power. Leading reactive power. So at the fundamental level, we have seen what is the reactive power from the power triangle, right? And then what is the reactive power polarity with respect to load and generator for the different loads like inductive load and capacitive load, right? Inductive load and capacitive load. Now, so let us go further. For example, so what is reactive power if I want to define? If I want to understand what is reactive power, so how can I understand? So for example, if I take the voltage as Vm sin omega t. So what is the voltage? Now I am taking V equal to voltage equal to Vm sin omega t, which is the sine function, and I equal to Im sin omega t minus theta. Let us assume that it is a Let us assume that it is a lagging load. It is operating under lagging load because theta is negative. So what does it mean? So if I want to draw the voltage and current here, how can I draw? So voltage is the pure sinusoidal waveform. Voltage is pure sinusoidal waveform, right? V equal to Vm sin omega t. Voltage is pure sinusoidal waveform, right? How the current will be? Current lag voltage at an angle theta. So now let me mark theta here. So lagging means after voltage, the current will start at an angle theta. Now this is the current. Let me represent with the other color. So this white is the current. Okay, we have drawn the voltage and current. This is the voltage, yellow is the voltage, and white is the current. Now I want to find how the active power and reactive power. So if I want to find the active power and reactive power, so how could I find? So for example, if I want to find that P of t equal to Vm sin omega t into Im sin omega t minus theta. Right? So the instantaneous power equal to instantaneous voltage into instantaneous current. Very simple. So voltage into power. So power equal to voltage into current. Now we got these two terms. So if I simplify and decompose into active power and reactive power, so this equation would be so P of t equal to Vm Im by 2. I am not deriving the expression here, simply I am writing, so we can derive it. So in the previous class we have derived. So now Vm Im by 2 into cos pi right, into 1 minus cos 2 omega t plus, not the plus, minus Vm Im by 2 sin pi into sin 2 omega t. Right? So which is very simple. But we need to understand how the reactive power performs, how the reactive power will be. Right? So here it is like Vi cos pi. So Vm Im by 2 is nothing but Vrms into Irms. So which is equal to active power. Right? So it is Vi sin pi. So let me mark all this as pi. Right? So we can make it as a power factor angle. So Vm Im by 2 into sin pi. So it is the reactive power. So now how I can write? So which is equal to P into active power component into 1 minus cos 2 omega t minus Q into sin 2 omega t. So this is an active power component and this is the reactive power component. These two are the instantaneous values, not the average value, and these two are the instantaneous values. Now if I want to draw these two, how it will be? So it is if I want to draw the active power, so it is active power or reactive power. Let me draw the reactive power first, which is equal to minus Q into sin 2 omega t. So how can I write? So it is minus Q into sin 2 omega t. Sin 2 omega t is nothing but 2 times of the fundamental frequency. If voltage completes one cycle, so this active power component or the reactive power component complete the 2 cycles. So it would be like this. So it is the reactive power. If I want to write the active power, so how can I write? So how can I draw? So it is 1 minus cos 2 omega t. If I substitute cos 0, it is, so initially it will start from 1 minus 1, 0. It will start from 0, and at 90 degrees it reaches to the maximum. So this is the 90 degrees, right? It reaches to the maximum, and then at 180 degrees it will be 0. At 180 degrees it will be 0. Again it reaches to the maximum. At 180 degrees it will be 0. Right? Now, so why we have derived all these things? Because, so we are mentioning that, while deriving or while defining active power and reactive power, so we are mentioning simply, so active power is unidirectional power, right? So reactive power is oscillating power, like that we are mentioning. But there need to be a proof. That proof is this one, right? So here it is a reactive power. So for example, if I want to find the average reactive power, right, from this waveform, let us find the average reactive power. What is average reactive power here? So here, if I find for one cycle, the positive area is equal to negative area. If I find the total area in one cycle, it would be 0, right? The average reactive power is 0. So average reactive power or average power, let me write it as a reactive power. Average reactive power is 0. Now, if I find the average power, so average active power, so what it would be the, so average active power equal to, so it is an average active power. So will the active power becomes negative? No, it is always positive. Remember this point. This point is most important. So the active power is positive, whatever may be the condition. For example, the active power always flows from the source to load. The active power always flows from the source to load. The direction of active power is always flows from source to load. So which is unidirectional, and it is always positive. Right? So if I find the reactive power, it oscillates. Sometimes it is positive and sometimes it is negative. So it is oscillates, right? So this is the reactive power. So if I find the average active power, so what would be the? It is Vm Im by 2 into cos pi. So what it is? Vi cos pi. Average power equal to, or active power equal to, or real power equal to, active power equal to V into I into cos pi. So these two are the RMS voltage and RMS current, Vi cos pi. So now let us see. So for example, I will take the reactive power here, active power here, reactive power here, so active power here. So what is the power type? What is the reactive power type? So which is oscillating in nature. Right? So what is an active power? Which is always unidirectional power. Always positive. Unidirectional power. And if I want to find the frequency, in both the cases, what is the frequency? It is cos 2 omega t, it is sin 2 omega t. So which is nothing but 2 times of the fundamental frequency. The frequency is 2 times of fundamental frequency. If F is the fundamental frequency 50 Hz, for example, so our supply frequency is 50 Hz. So what is the active power frequency? Instantaneous active power frequency. So it is 100 Hz. What is the instantaneous reactive power frequency? It is also 100 Hz. It is 2. Now average value. If I find the reactive power, so average value it is 0. And if I find the active power, it will be the Vi cos pi. It has an average value and it is always positive, right? So reactive power can be negative or positive. It depends on load, right? It depends on load. But active power is always positive. It will always flows from the source to the load. Source to the load, right? Now let us discuss with the different applications. What is active power and what is the reactive power? And let us discuss the different applications so that you can understand clearly. You can understand clearly. Now let us take our first application is transformer. In a transformer, so let us explain the working of transformer in terms of with respect to reactive power. So what is the function of the reactive power in transformer? So now to explain that, so let us consider the 4 different cases. No load, right? So let me take the 0.8 lagging and unity power factor load and 0.9 leading load. I think all the loads has covered, right? All the different conditions has covered. So we took as the no load and the 0.8 lagging, unity power factor and 0.9 lagging. First, let me take the no load condition. So what is the no load condition in a transformer? So the no load condition in a transformer is nothing but the secondary has not connected to any load, any electrical load, right? So if secondary is not connected to any electrical load, so the secondary current is 0, that is load current is 0. The primary requires the current is only the no load current, which is magnetizing current, right? Magnetizing current. And this magnetizing current is also called as reactive current. Why? Because it is the reactive component of the no load current and it is exactly 90 degrees out of phase with the voltage, right? So it is called as reactive current, right? So now so if what is the function of the magnetizing current here? To produce the magnetic flux in the core and to maintain the magnetic flux is constant with respect to with respect to variations of the load. So whatever may be the load, it has to maintain the core flux as constant. So the magnetizing current is here. So here, so the magnetizing current is derived from the source, right? It came from the source. Now, so let me explain with the no load. So now we got the magnetizing current, right? So generally here, so no load power factor is less, right? The no load power factor angle in between the 70 to 85 degrees. So the no load power factor is less. So the sin pi naught is more, which means it draws more reactive power. It draws more reactive power from the source. The no load reactive power is more and it is derived from it is taking from the source. So it is taking from the source. Right? So now, in a simple terms, what is the function of the reactive power in a transformer? So the function of the reactive power in a transformer is to produce the flux in the core and it has to be maintained constant and the flux has to be maintained constant. Now, for example, if I consider 0.8 lagging load, now I connected the load, let us connect the load. Now I connect the load. So let us assume that it is a 0.8 lagging load. So now what is the reactive power? Will reactive power increase or decrease? So let us see. So it is a lagging reactive power. And to compensate this lagging reactive power, so it requires lagging reactive power. It has to taken from the source. So the additional reactive power has to be taken from the source. Here the transformer is, understand here the transformer is a simple messenger which connect the source and load. The additional reactive power required by the load also taken by the transformer in addition to the magnetizing reactive power. So clear? So in addition to the magnetizing reactive power, so it has to take the load reactive power, load VAR also it has to supply. Next, third condition is UPF, unity power factor. So unity power factor is nothing but resistive load is connected. If the resistive load is connected, what happens? If the resistive load is connected, it operates on the unity power factor. There is no requirement of reactive power. So it is, since it is a resistive load, so only the magnetizing reactive power is sufficient. So the reactive power is magnetizing reactive power. Magnetizing reactive power. QM is the magnetizing reactive power. Now, let me take the 0.9 leading. So what is the leading? So leading means we have connected the capacitive load at the end of the transformer. If I connect the capacitive load, what happens? If I connect the capacitive load at the secondary side of the load side of the transformer, so what happens? So the capacitive leading reactive power will compensate the, so here whatever be the losses caused in the primary Ix reactive drop will compensate the reactive drop and will take the less reactive power. So from this source, we need to give the load reactive power, which is very less when compared to the lagging reactive power. In addition to it has to be magnetizing reactive power. Magnetizing reactive power. Now, so let us conclude this. So the no load reactive power is QM. And here, when compared to these two cases, what happened? So the lagging reactive power has to take the more reactive power from the source. This will be more when compared to the leading reactive power. So this is how the reactive power, so affect the magnetic flux and maintain the constant magnetic flux. So now let us analyze the induction motor. So how the induction motor will work? So I am not explaining complete working and all, just to understand the reactive power role, let me explain the induction motor. Now, so here this is the stator, assume that this is stator and this is the rotor, and for this rotor let me connect the load, mechanical load. Right? So it is a simple circuit if you understand. So it acts as the induction motor, acts as an inductive load. It takes lagging VAR, lagging Q lagging from the source. Let us analyze this also. For example, consider the four cases. No load. And one more thing, let me take the full load. Full load condition. And if you overload the induction motor, what happens? Let us see that. If you overload the induction motor. Okay, the three cases are there. So in the similar manner, similar to transformer, so the main function of the reactive power is to produce the air gap flux, and to maintain the air gap flux as constant. So to produce the air gap flux, the reactive power function is to produce the air gap flux. But if we consider the no load condition, what happens in the no load condition? In the no load condition, so if Ns is the stator speed, rotating magnetic field, so Nr is, let us assume that rotor is rotating with the Nr. So what is the slip? Slip is difference between the Ns minus Nr. So Ns minus Nr. So when induction motor is not connected to the load, any load, so what happens? The rotor rotates near to the synchronous speed. The slip is very less. So when slip is very less, so the active power requirement is very less, because slip is directly related to the active power. Similarly, the copper losses also, so rotor copper loss also depends on the slip. So now, in the no load condition, if active power is less, what about the power factor? So the power factor also, it will operate at the low power factor, right? It will operate at the low power factor. If it is operating at the low power factor, so what about the sin pi? Sin pi naught, the sin pi naught is more, it draws more magnetizing current to establish the flux there. So the reactive power requirement is more. The reactive power, let me call this as a Q naught. The reactive power requirement is more. So it is very simple. So here the reactive power is there. So the reactive power function is to produce the air gap flux. And how the reactive power will be? In the no load condition, there is no load is connected to the rotor. So when no load is connected to the rotor, so load is not connected to the rotor. So the NR is similar, same as NS almost. The slip is very less. So the only component is the reactive power. And it is more, right? Because there is no active power. So to have the total power, the only reactive power component has to be there. So it has to be more. The Q naught is more. Now let us take the full load. Let us assume that it is 3 to 5% of slip. It is operating in a full load. So for example, so in a full load condition, so what is NS minus NR? NS minus NR. So now induction motor is there, rotor is there. Now I connected the load. So what happens? If I apply the load, what happens? The rotor will slows down. So the rotor speed will reduces, the slip increases. So some power will be taken by it has to be taken active power also from this. So the active power also there. So when compared to this, so the reactive power requirement is less. So the reactive power requirement in the induction motor, when it is operating in the full load, is less than when it is operating in the no load because of slip. So for example, if I overload this, let us assume the slip is 9 to 10%. So what happens during this condition? If I overload the induction motor, what happens? It draws more current from the source. The stator current is more, which causes, if the current is more, which causes I into X, the stator voltage drop is more. To compensate this, so what is this? To compensate this, it has to take more reactive power. It is overload, right? It has to take more reactive power from the source. So in an induction motor also, the role of reactive power is significant. When it is operating in the no load, it has to be take more reactive power from the source, and when it is operating in the full load, the slip will be increases. So the some power will be shared by the active power, right? So the reactive power requirement is less when compared to the no load condition. So but if I increase further after full load also, if I load the motor, so what happens? The current is increased drastically, so here the stator voltage drop increases. When stator voltage drop increases, so to maintain the constant flux, it has to take an additional reactive power from the source. The reactive power again increases. So this is how in an induction motor the reactive power will be. The reactive power analysis can be done. Now let us take the synchronous generator. Synchronous generator. Now, if I take the synchronous generator, so what is the expression for the Q? So the expression for the Q is E cos delta minus V divided by X into V. Right? So the expression for the reactive power will be like this. So we are not going into more detail, but let me explain you how the synchronous generator operates. How the synchronous generator operates, in which parameters the reactive power will be dependent. Now generator is there. So here there are three conditions are there. Let me take over excitation, under excitation, so normal excitation. Let me take these three cases. Now, so what is over excitation? The excitation should be more than the terminal voltage. So what is that? When E cos delta is greater than the V, so we can call this condition as over excitation. So in this over excitation, when it is E cos delta is greater than V, so how it will be? This becomes positive and the reactive power is positive. If I find the reactive power is positive. If I find the reactive power is positive, because it is generator, it delivers lagging reactive power. Right? So now, so if I consider the under excitation. So in case of under excitation, so what is the condition? When E cos delta is less than V. So when negative value is greater than the positive value, this total term becomes negative. That is, Q is, the polarity of Q is negative. When Q is negative, it delivers leading reactive power. So now, next one, the normal excitation. So what is the normal excitation? So normal excitation is nothing but E cos delta equal to V. So what is the reactive power now? The reactive power equals 0. It neither delivers nor absorbs. It doesn't deliver and it doesn't absorb. Right? So now this is how the reactive power will be in case of generator. So now these are the three cases. And one more thing is, in a synchronous generator, if you want to control the reactive power, so we need to control the excitation. If you want to control the active power, we need to control the prime mover input. Now, the next one. So now when I read power electronics, I got the doubt is, so here in a networks I studied as when I connect the resistive load to the system, it will operate in the unity power factor. But if I connect the resistive load, let us assume that it is a full wave rectifier. So if I draw the voltage, how the voltage would be? So let me draw the voltage and current. Let us see it is operating in the unity power factor or not. So for example, it is voltage, input voltage, which is equal to Vm sin omega t. So how the output voltage? If I trigger at an angle alpha, so the output voltage will be like this. Right? The output voltage will be like this. Right? So this is the output voltage. This is an input voltage. So at this stage, understand like this. So whenever I trigger that, so the output voltage will be like this. So when alpha is the triggering angle. Now I got the output voltage and the input current. So if I find the output current, How the output current? This would be like this. This would be like this, white color. So if I draw the source current, now if I draw the source current, which is very important. So fine, observe it. So the source current will be like this. Source current will be like this. Now this is the source voltage and the source current. So if I remove this one, the voltage and current are in same phase. But if I add the power electronic circuit, I introduce an angle in between as an alpha. There is a phase angle, so which is equal to alpha. So if phase difference is there, there would be active power as well as reactive power. So what does it mean? Even though I connect the resistive load, so because of the power electronic circuit, because of the switching circuit, so what happens? There causes a phase difference between the voltage and current, so which causes the reactive power requirement. The source has to deliver the reactive power. The source has to deliver the reactive power. So based on the load requirements. So based on the firing angle, so the reactive power will change. In the power electronic circuit also. So in the overall, let me conclude the session. So if I take the reactive power, in a complex power, if I consider this, it is an imaginary power. The next one. So in a power triangle, if I consider it is the sine of the Vi sin pi. So that is, it is also a reactive component. So if I consider the third case, the reactive power is also called as an oscillating power. The average power of the reactive power is equal to 0. It doesn't carry any work like active power. So it involved in the process of work, but it doesn't carry any work. So which is called as reactive power. And it has the 2 times of the fundamental frequency. If you take the transformers or induction machines, depends on load conditions, the reactive power requirement varies. So the main purpose of the reactive power in case of the transformer or in case of the induction machine to produce the flux, to produce the working flux. In case of synchronous generator, based on the excitation, it delivers the lagging reactive power, it delivers the leading reactive power. For example, if you consider the synchronous motor, an overexcited no load operated synchronous motor operates as a synchronous condenser. So it can also act as a condenser also, right? So based on the reactive power requirement, so it will be used. So what is the function of the reactive power in whole sum? So the function of the reactive power is to produce the flux in the machines, is to maintain the output voltage as constant. So it is used in the voltage regulation, and so it can be used in the stability improvement process. It can be used in the power factor improvement process. So for example, if I increase the power factor, what happens? So for the same power, same voltage, if I improve the power factor, to carry the same power, the current requirement is less. So the size of the conductor also reduces. So this is all about reactive power. So why I have taken the separate class for reactive power? So I have seen in the YouTube or social media, the reactive power is explained like lace packet or the air filled balloon. Like the tire has the air, inside the air is there, but tire is working. Like that, different analogies I have seen. The main concept is deviating. So if you apply the analogy with the different practical applications, right? So wholesome, this is the reactive power concepts. I think I have cleared all your doubts. So which can be, it can be useful for your interview questions, or it can be useful for your MCQs, multi-choice questions, right? So here, let me help you with your preparation. So in the next coming lectures, what I am going to teach in the next 60 days, I will give you the schedule. I will cover as I said before, I will cover all the topics in the power systems, electrical machines, control systems, power electronics and networks. Right? Thank you so much. Thanks for attending the session.